morning, everybody. It's 9 o'clock. So I think we should start this Thursday session, which is mostly about electron-phonon interaction in harmonic materials. And also we'll talk about superconductivity. So first we have like a lecture given by Giovanni Marini, and then we have two different hands-on sessions on how to calculate electron-phonon interaction and combine it with SSCHA. Okay. So yeah, I think we are still, I still have a lot of people. Okay, we need some people, I think, still, but it's good. I know the conference dinner yesterday extended it, so that's normal. Okay, good, Giovanni. Thank you.
Thank you very much. Good morning, everybody. And I'm very happy to be here and to talk about a very important topic in solid-state physics, namely the topic of electron-phonon interaction and in some sense also of superconductivity. And first of all, I would like to focus your attention on why are we talking about this, why is this important. And actually the idea is that in solids we know most often we are interested in electronic properties, but we are also interested in nuclear properties, in the properties of the lattice. And as you know, the lattice has a very important effect on the properties of the solid. And what is also true is that in quantum theory, you can imagine the movement of the lattice as being characterized by a quasi-particle, so the phonon, which you know very well, better than me probably. And essentially the idea is that, okay, you have these electrons, these phonons, so as both of them are essentially related to electromagnetic phenomena, there is no reason why these particles shouldn't interact among themselves. And so it's important to understand what is the effect of this interaction on the properties of material. Like the second question indeed is exactly this: is electron-phonon interaction something relevant, something that you want to study, or is it something that is not relevant? Well, actually, I hope I will convince you that it is for many, many different kind of applications. And I want to do some example, just to give you some context on why we are doing this. First of all, if you think about metals and you are interested in electronic transport properties, you will see that essentially, if you consider the behavior of the resistivity of some metal and you consider the most important interaction at any given temperature, you will see that essentially in a very, very small range, the electron-electron scattering can be relevant when the temperature is close to zero. But then in the larger possible range, it's all electron-phonon interaction, essentially. So consider that, for example, for electronic transport properties, electron-phonon interaction is substantially the most important contribution. This is, of course, in the case of clean metals, so where there is no impurity. Also, another important example is superconductivity. I won't be talking too much about this now, but essentially, as you know, the conventional mechanism for the effective attraction that you need in solids to get superconductivity is mediated by the interaction of Cooper pairs given by phonons. And this is relevant also for many, many different technological applications as well as fundamental understanding of the matter, essentially. So this is not all, because, for example, you know that semiconductors, when you go measure the gap as a function of the temperature, you will observe that the gap has a strong dependence on the temperature of your system, and in particular, it gets lower as the temperature is increasing. And also, this can be interpreted in terms of the effect of the electron-phonon interaction. Also, still talking about electrons, when you go and perform some RPS measurements, so essentially you are doing the photoelectric effect on materials, and you measure the quasi-particle, the electronic excitation, and you will see that basically RPS gives you access to, by measuring the binding energy and the momentum of your particle, will give rise to a dispersion. But when you go on and look at the measures, actually you will see that you do your DFT calculation, predicts, like, for example, a linear dispersing band, and then you go and perform the measure, and you see that there are kinks in this dispersion. And this kink is, you can interpret this kink very often in terms of the self-energy due to the electron-phonon interaction. We will come back to this a little bit later. Also, as Professor Mario was talking in the first lecture about harmonicity, you can also measure phonon, of course, with different kind of scattering probes. But let's talk about, for example, X-ray scattering, when you have access to a large range of Q vectors for the phonon. And it's true that in anharmonic materials, the line width of the phonon is related to the anharmonic contribution, and so the reduced lifetime of your quasi-particle. However, in materials where electron-phonon interaction is strong, you would see that a contribution to this line width also stems from the electron-phonon interaction. And this is important also because essentially it's a way to measure it. It's a way to measure the electron-phonon interaction. For example, this is magnesium diboride, and this spectrum is essentially completely interpretable in terms of electron-phonon interaction and not in terms of anharmonicity. So let's say the two things are both important and both contribute to the phonon line width. Is essentially the idea is that you have different mechanisms by which the phonon can be destroyed, and so by which the lifetime of the phonon can be diminished. One is, of course, the anharmonic decay into two different phonons, but another one is just the decay into an electron-hole pair, and both of them contribute to this line width here, let's say. So this is not all, because also charge density wave materials, still measuring phonons. So now not the imaginary part, not the spectral function, but just consider the real part of your excitation, and you will see that when you're approaching the charge density wave transition, the phonon frequency will get renormalized, and this renormalization can be interpreted in the framework of a contribution to the real part of the self-energy of the phonon, still stemming from electron-phonon interaction. But this is a complicated topic, and I will discuss a little bit later in more detail onto why, for example, if you do your calculation in the FT, you get this effect actually, but it's very wrong. And the reason is harmonicity, of course, as we already mentioned in the previous lectures. Also, last example, for example, if you go on and perform measures on silicon, and you know that silicon has a direct gap of 3.4 electron volts, so you would expect that the optical absorption starts at that value, but actually in reality the optical absorption starts at 1.2 electron volt, and this is why there are also it is also possible to a higher order of perturbation theory to imagine processes where the direct optical transition is also accompanied by a phonon emission that allows you to absorb at even lower energy values, just because you have an indirect gap where you can relax to. So all of this is just to give you an idea of why are we studying electron-phonon interaction, and why it could be desirable to understand, to have a microscopic understanding, and also the possibility to quantitatively calculate this quantity and see what's its effect on material properties. So I will start just by giving you a microscopic idea of where this term comes from in the Hamiltonian of our crystal, and then we will go on and consider the different effect on different phenomena in solid-state physics. So let me start by the Born-Oppenheimer approximation, and this is where actually everything begins, of course, because we have a crystal. This is just simply a notational slide where we have the generic crystal size is described by an index, a cell index, and of course the position of the atom in the cell. And we can write our Hamiltonian as the sum of kinetic and potential terms, both for the nuclei and the electrons, and of course there is also an interaction term between the nuclei and the electron. So the first part is the purely ionic part, and this potential is nothing but the Coulomb potential between different nuclei. Then you have another part containing the kinetic term for the electrons as well as their interaction. And finally you have a term that contains the interaction between the electron and the ions. And this term is what we usually call the bare electron-ion interaction. And of course, this is very important for the electron-phonon interaction. We will take a little bit of a different point of view because we want to know, we want to switch to a different kind of framework in order to understand this Hamiltonian. And what we do usually is to consider an electronic Hamiltonian where you essentially have your kinetic plus potential term for the electrons, and all the other terms, so the bare electron interaction and the nuclei potential, are considered as an external potential acting on the electrons, a static external potential. So if we go on this route, we will see that we can actually write the total wave function for our system in terms of a nuclear wave function that depends on time and also depends on the position of the nuclei, and then an electronic wave function that depends on the position of electrons on the ions and of time. And you can demonstrate that this factorization is in principle exact. You can factorize exactly this wave function in this way. And if you do this, and then you do a little bit of mathematics just to isolate, let's say, just to try to isolate the nuclear wave function in such a way that you can obtain an equation for the nuclear wave function. So with some algebra, you can see then you multiply by electron wave function just to integrate out the electronic degrees of freedom. And you will see that at a certain point, you will come to an exact equation still containing essentially the action of the kinetic nuclear operator onto the electronic wave function in different ways, the action of the nuclear operator on top of the nuclear wave function, and also another term, this E here, which is the Born-Oppenheimer surface, which is essentially the electronic Hamiltonian that we defined before, evaluated onto the electronic wave function. So in principle, this is done for a very precise reason, and the reason is that here you can solve an electronic problem that post-solution gives you this term, which is then plugged into this nuclear problem, and then you can solve also the nuclear problem. So it's a way to decouple the two problems. Of course, you can't do the decoupling very well now because you still have some terms, but okay, who cares? We just neglect them. So let's neglect the effect of the kinetic nuclear operator onto the electronic wave function and see what happens. And what happens is that if you neglect these two terms in the equation, you remain with an electronic problem whose solution are this psi n, ionic problem, which is basically the kinetic operators plus the Born-Oppenheimer energy surface, and then you can solve this problem, for example, in an harmonic approximation to a first approximation. And essentially you get this vibrational Hamiltonian. Then you can, depending then on the treatment that you do of this Born-Oppenheimer energy surface, you have different kinds of accuracy. And of course, I won't go on into this because it's basically one of the aims of all the other talks, but this is very important, of course, for us. But let's stick to the harmonic approximation for now. And let's consider now what is the remaining interaction between the electrons and phonons. Of course, as soon as you neglect all these terms, you don't have any residual interaction, besides the fact that, of course, the electron is still feeling the nuclear potential in their Hamiltonian, but there is no interaction with the motion of the phonons, of the nuclear, so with the phonons. And so the way to actually introduce electron-phonon interaction is to retain some of these terms in perturbation theory. So we go on and we consider these terms. There are two terms, and we want to go about and see what's their importance. And in particular, we're interested to the linear order of this interaction. So we'll just retain terms that are linear. And there are different ways to go about this, but one way to do this is just to expand your electronic wave function as a static wave function that corresponds to the electronic solution at the equilibrium position, plus some perturbation that you can evaluate in the standard Schrödinger relay perturbation theory. And essentially, you will see that some terms appear, and in particular, that the perturbation depends on the variation of the electronic Hamiltonian as a function of the nuclear motion. So we would like to retain only this first term here, and then to plug the correction to this wave function into our problem and see what kind of terms stand out from this Hamiltonian. And we do exactly that. And we see that in the first term, so the term containing the action of the kinetic nuclear operator onto the electronic wave function, and another term containing the average of the valuation of the nuclear operator onto the nuclear wave function, gives rise to actually a finite contribution, which is retained in our approximation because it has linear dependence onto the nuclear motion. And okay, you have to do a little bit of mathematics in order to understand what's happening here. However, it's pretty easy to understand that the kinetic motion of nuclei is actually can be related to a spatial derivative of the Hamiltonian, of the electronic Hamiltonian term. And essentially, so this perturbation that we saw before, this one here, gets derived by the action of this operator, and gives you essentially the expectation value of the spatial derivative of the Hamiltonian with respect to nuclear motion, which is evaluated onto the static wave function, so the one that you have at equilibrium position. And see, this is the first term up to a linear approximation in the nuclear motion, which we retain for electron-phonon interaction. So this is indeed the interaction between the motion of the ions and the electronic Hamiltonian. Then we also have another term, this one here, but as we are essentially evaluating the effect of a second derivative onto the second spatial derivative onto things that depend linearly onto the displacement, this term is zero in up to the linear order. Then if you expand your wave function to higher order, you will have also a contribution from this second term. Of course, this is not the only way to obtain an electron-phonon interaction, because this is a perturbative way, but there are also many other ways. And for example, Raffaello and Jon now are working on a non-perturbative way to include the electron-phonon interaction in this Hamiltonian. Also, now we just need to a little bit rearrange our H1 term that we derived, so the only one that survives our linear electron-phonon interaction treatment. And I don't want to go too much into mathematics onto this, but essentially it's very important just to notice that, okay, here you have the spatial derivative of the electronic Hamiltonian. Here you have you have to evaluate the kinetic operation to the nuclear wave function. But if you impose that, okay, this operator here can be recast in terms of the commutator of the positional operator and the Hamiltonian, on the vibrational Hamiltonian, and at a certain point, essentially, as these are eigenfunctions for the nuclear problem, you will have that the eigenvalues coming out from the application of this Hamiltonian onto these wave functions will give you the difference of the energies of the phonons, and this will be exactly cancelling the difference in the energy of the electron, just because we want a scattering that's conserving the energy. So going about onto this simplification here, you will remove this denominator here, and you will remain still with a term that consists essentially in the derivative of the electronic Hamiltonian onto the nuclear motion of nuclear position, and this is what we usually refer to as a deformation potential in real space. But actually, we would like to also to have a practical way to treat this problem. And what we do is we write the positional operator for the nuclei in terms of creation and destruction operators, and we write it in Fourier representation in such a way that essentially we can disentangle different Q contributions. So we write the sum over the wave vectors of creation and destruction operator, which is possible to do, of course, in the harmonic approximation of this problem. And we come to this form that contains creation and annihilation operators, and this derivative of the electronic Hamiltonian in terms of the nuclear position. And if we go on about and just rewrite this term in Fourier transform as well, we will see that essentially we can obtain an expression where both the phonon operator and the derivative of the electronic Hamiltonian are done onto the same wave vector. At this point, we are ready with this expression here, which is becoming pretty similar to what we usually use. We are coming to an expression that can be used to be quantized in second quantization for the electrons, and this is possible to do because essentially this is a one-body operator that can be expressed in terms of its component onto the chosen basis set, and then of course you go and plug the creation and annihilation operators of the electrons. And in a solid, we also do use a specific wave basis set for this operator, which is essentially the block wave functions, and you arrive to an expression which is essentially is containing the derivative of your Hamiltonian, which is evaluated onto the periodic part of the block functions. And we are also now writing that as usually what we do is as electronic Hamiltonian, we're considering just the like the kinetic electronic term plus the constant term, but the only spatial dependence is on the constant potential. And also when we do linear response, which then we use we usually use just to start about our electron-phonon treating, we just perform a monochromatic perturbation, which just depends on one Q. And so we basically evaluate this for a specific Q, this matrix element here, and we come to an expression that is what we usually call the electron-phonon matrix element, and this is the central quantity that is characterizing our treatment of linear electron-phonon coupling. This quantity is now what I want you to focus your attention on, because it has a dependence on the frequency of the phonon at the denominator. I won't go into too many technicalities about what is this frequency here. And then you have basically a matrix element of the derivative of the constant potential evaluated on the periodic part of the block wave function. So this is a matrix that depends on many different things. Depends, for example, onto the phonon index. So this is the phonon index. These are the electronic bands, and this is electronic momentum, and this is the phonon momentum. So it's a pretty complicated object, but as we will see, it's a fundamental object that we can actually calculate in practice. And you can see why we can do that, because we know actually how to evaluate this quantity in density functional perturbation theory. So the standard way to go on and calculate this kind of quantity is just to perform a standard density functional perturbation theory calculation at a certain momentum q. And then, of course, you basically get this matrix element for free, as long as you have converged this term here, let's say. So, at the end of the day, the electron-phonon Hamiltonian is just the bare electronic Hamiltonian plus a vibrational Hamiltonian and an interaction term, which is the electron-phonon, which is, as you can see here, is composed by an electron creation operator, an electron destruction operator, and the sum of a creation and a destruction operator, destruction and creation operator for the phonons. So at this point, our problem is set up, and we can use this setup to start studying the effect of this interaction to different parts of our physical problem, which can have many different take different forms. So I will start by talking about the effect of this interaction onto the electronic degrees of freedom first, and then we will see also the effect of the interaction on the phonon degrees of freedom. So differently from what we did last days for anharmonicity, where we focus our attention only on the lattice properties and the effect of the anharmonicity on lattice properties, here we need to be careful, because being an interaction, the effect of the interaction is visible both on electrons and phonons, of course. So let's start with the electrons. So actually the formalism is pretty similar to what you have seen in past lectures, especially in the lecture given by Raffaello for the spectral function, and is about the relationship existing between the bare propagator, both for the electrons, which is this D here, and the phonons, which is this D here, and their counterparts in the presence of an interaction. So, for example, you know that the effect of the interaction on the electrons, which is this left part of the screen, is just the appearance of an electronic self-energy, which is just defined as the difference of the inverses of the bare and the interacting propagators. And the same can be said for phonons, essentially. So it's basically the same idea applied to both kind of particles. And let us focus our attention now on the electronic self-energy and what are the effects that we expect from it onto the electronic properties. So, as we were also seeing yesterday, essentially in the absence of interaction, when you have like an infinitesimal parameter eta, which is just representing a very small broadening, you expect essentially a Lorentzian behavior for your spectral function, which is just the imaginary part of the green function. And this particle, this spectral function, should be picked exactly at the bare electronic eigenvalues. So at this point, we now start to introduce some interaction gradually. So first, we will assume that the interaction is small, and also that the imaginary part of the self-energy is much less than the real part. In this way, the interaction can be still considered as a simple shift of your quasi-particle peak, which will acquire, just because in this denominator you get this shift due to the real part of the self-energy, and you will acquire essentially a different value for the peak of the Lorentzian. But still you will retain a Lorentzian kind of form for your spectral function. Well, when, as we saw yesterday, when this is not true anymore and the imaginary part becomes not negligible, you can have situation in which the quasi-particle peak, in this case the electronic quasi-particle peak, remember we're talking about electrons here, is not a Lorentzian anymore, and it acquires the most different forms and profiles. And this is just the effect, of course, of the fact that that you're opening essentially scattering channels. But of course, we still are not talking about the effect in a let's say in a real matrix element. As you know, the spectral function is proportional to many different intensities that you measure in experimental setups. So as we are talking about electrons, let's consider an angle-resolved emission experiment. And in this case, what you expect is exactly something like we saw in the introduction, where you have some kinks or deviations from the bare electronic dispersion. So at this point, we will also consider some realistic form for this correction, and in particular, let us focus on the limit where you can linearly expand your self-energy around the quasi-particle peak, the renormalized quasi-particle peak, and also assuming that the imaginary part is still a little bit smaller than the real part, in such a way that we can retain a quasi-particle interpretation, we will observe that the effect of this self-energy is essentially, we are just retaining here the linear term of the Taylor expansion around the quasi-particle peak, and we will see that essentially we expect a rigid shift of the spectrum plus this linear term here. And this linear term here is very interesting because it contains a quantity which is very important for us, as we will see, which is called the mass enhancement parameter. This parameter is the frequency derivative of the real part of the self-energy evaluated at the quasi-particle peak. And there is a precise reason on to why this is called the mass enhancement parameter. And the reason is that if you now go on and derive with respect to the momentum the expression for our renormalized peaks in our spectral function, you will see that essentially this becomes an equation for the new velocities, the dress velocity, let's say, dressed by the electron-phonon interaction with respect to the bare velocities. And you will see that this equation contains a factor. And as you can demonstrate that this lambda k is always greater than 0, essentially the effective velocity is always reduced. And of course, from this we can derive easily that the effective mass of your particle in the presence of electron-phonon interaction is always enhanced. And so the reason why this term here is called the effective mass, the mass enhancement parameter. And this is really important, and it's it's evident in what we see in the Arcus experiment. Of course, this is the expected you would schematically that you would expect. So imagine that you have this linear dispersion in the momentum. You plug the electron-phonon interaction, and you will see that the velocity will get renormalized and the mass will be enhanced. And this is exactly what is happening to the red curve with respect to the bare black curve here. This can be measured, and it's for example in carbon system, it's very interesting because essentially as you can move the, for example, imagine graphene or graphite, and you start intercalating, for example, alkali atoms, so you start shifting your Fermi level. As this term depends importantly on the position of the Fermi level, you will see that essentially the mass of your particle, of your electronic particle, change as a function of the doping, of the alkali doping. And this is also interesting because, as I was mentioning also before for the phonons, also here for the electrons, these kinks gives you access to the intensity of the electron-phonon coupling in your material. So it's very important to be able to have a quantitative understanding on what is this electron-phonon coupling as a function of the doping. Okay, this is also true in superconducting system. For example, you know, magnesium diboride is very famous superconductor, and if you go and measure the electronic dispersion, you will see this kind of kinks here that are exactly that, are just the electron-phonon interaction as a selected electronic momentum. So let's now speak a little bit more about the fact that also we have an imaginary part due to the electron-phonon coupling, and that this imaginary part is nothing but essentially the scattering time, or the line width, if you want, of your system, of your electron. But from a practical perspective, what is this term? Because right now we just said, okay, if there is a self-energy, there are some effect on the electronic bands. Okay, but what is this self-energy? What is, from a mathematical point of view? So to the lowest order, the electron-phonon self-energy on the electrons is just this diagram here, where you have an electronic propagator and a phonon propagator. And this diagram here is what's called the van Migdal term. And we are retaining just this right now. We are not going into complicated things about the vertex and any other like more higher order effects. And if you retain just this diagram here, when both vertices are just electron-phonon interaction, and you have some to multiply them, okay, you have to sum them onto all the possible phonon momenta to a fixed, for a fixed electron, and then you have to multiply for some occupation factor that actually depend on the occupation of phonon and electrons, as well as the denominator, which is is picked where basically around the electronic energy, because this is usually negligible with respect to this. And this is, of course, at the occupation that I was just talking about. So the real part that we just were discussing now is just the principal value of this of the quantity that we were just mentioning, and the quasi-particle corresponding to this are nothing more than essentially the shifted bare electronic values by a quantity that is essentially the real part of the self-energy evaluated at a frequency that is equal to the quasi-particle peak. Similarly, for the imaginary part, we essentially end up with an expression that contains the delta functions that are centered onto the electronic energy minus the phonon energy, multiplied still by the square of the electron-phonon matrix element, and this is exactly why this is so important for your electronic properties. And this expression is simply basically what you will get if you would apply first order Fermi-Golden rule to the electron-phonon problem. So at low temperature, basically you can neglect the occupation factor coming from the Bose function, and you will get that the imaginary part of the self-energy of the electrons retains this form here, and this form is very useful to evaluate, for example, the lifetime of your carriers in, for example, it's in semiconductors. So when, for example, you have some excitation and you want to see what's the typical time that they employ to recombine in and to go to the minimum position of the band, you will just do a calculation that involves the lifetime. And for example, you can consider only some processes here. So it's not like, for example, imagine that you have an electron in a out of equilibrium position in your conduction band in your semiconductor, and you want to evaluate how much time will it pass before it goes back into the minimum of the conduction band. And the way to calculate that is just to evaluate this imaginary self-energy here, essentially. Also, this is a good occasion to also introduce another important object in electron-phonon theory, which is the Liebesberg function. So at the beginning, what you do is basically to rewrite the imaginary part of the electronic self-energy in terms of this wave function, of this function here. And this function is proportional to the square of the electron-phonon coupling matrix element, and also contains a delta in the frequency. And with this mathematical trick, you can basically rewrite the imaginary part of the electron self-energy as an integral onto the frequencies of different terms. I don't want to, so basically the plus and the minus correspond just to the plus and minus form, so emission and absorption of the phonon. So I don't want you to focus so much on this expression because we are not going to deep into this now, but this is just a way to introduce this function, which become important in the next few slides that you will see. So the first thing that we do here, just to simplify a little bit the math, is to say that, okay, we can neglect this frequency dependence here just because the electronic energy is much, much bigger usually than the phonon frequency. Neglecting this, we come to this expression for the Liebesberg function, which does not depend anymore on the absorption or emission of the phonons. So this symmetric expression here gives a simplified expression for your imaginary part of the electronic self-energy. And if you go to the t equals 0 limit, you will come to an expression which is symmetric and which is essentially 0 before your phonon frequency, and then it becomes increasing as a function of the frequency. Now, the interesting thing about this, which is I was a little bit fast in this just because I don't want you to focus on this aspect here. But what is important is that if you start your expansion in temperature, so you will start expanding this occupation here to the linear order, the phonon occupation to the linear order, and but you assume that you're still in a temperature which is low enough to consider the electronic occupation as the theta functions. You will see that you expect actually a linear dependence onto temperature for your imaginary part of the electronic self-energy. Also importantly, this linear dependence is then multiplied for a quantity, which here we call lambda. And as you notice, this notation is very similar to the one that we use for it's the same actually, that the one that we use for the mass enhancement parameter, just because the two quantities are related and basically the same actually. It's a little bit tricky to demonstrate that, but it's just maths. It's basically this parameter here, it ends up being exactly the same mass enhancement parameter, which was the derivative of the real part of the self-energy. So the important thing here is that you retain this temperature dependence for your imaginary part of the self-energy, and this is also proportional to lambda. And as you can see, in real experiment, you actually observe that. And this is another way, so the derivative of this just gives you the electron-phonon coupling in another different way. So it's another way to measure the lambda k. So by measuring the derivative of this curve here, you can actually access still this lambda here. And this lambda here is nothing but exactly the same that we defined before for the real part. So this is all for the electronic part of the effects of electron-phonon interaction. And let me now switch to the effect on the phonons, which are probably is the main focus of what we will deal with today. The effect of the phonons we start from a similar perspective. So we start from the bare phonon propagator, and we want to have an expression for the interacting phonon propagator, which can be expressed in terms, of course, of the Green function and of the phonons, as well as to a first order a diagram that contains an electron and a hole propagator, and which is usually referred to as the bubble diagram. And at certain point, what you can do is to write the interacting propagator for the phonons, in terms of still the bare propagator and the self-energy, just as we did for its electronic counterpart. Of course, now it gets a little bit trickier because we already saw the effect of the anharmonicity onto phonon propagator. So this is a different aspect of the same problem in a way. So let's say that this pi here is the self-energy due to the electron-phonon interaction. This self-energy to first order, as we saw, is just the bubble. And this is a very important object in our treatment of electron-phonon interaction because it contains, besides containing the square of the electron-phonon matrix element, it contains electronic occupation in K and K plus Q. And as we will see, this is very important for us. In particular, we know that in order for this term to be non-zero, you should have that the occupation of the K momentum and n band should be different from the one at K plus Q m. What does this imply? This implies that essentially, think about a semiconductor. This term would be non-zero only if you are considering an electron in the valence band, for example, a hole in the valence band, and an electron in the valence band, and an electron in the conduction band. So you would have zero contribution if you were taking both electrons from the valence band, just because this would get identically equal to zero. But this has important effects, and this is exactly the reason why this self-energy here is particularly important for metals. The reason is that consider now the case of an insulator. Okay, let's consider the real part of this self-energy now. Regarding the real part, we will have poles, and the poles will be centered essentially. If we now consider this difference here in an insulator, this difference will be bigger than the gap of the insulator, because as we saw before, we are just evaluating these terms in the case where one electron is in the valence and one in the conduction, because if both are in the valence, this term is zero. So what happens actually is that this big denominator here, which is basically the gap, because now h bar omega is very, very small, becomes very large, and so this means that this term becomes very, very small in semiconductors and insulator materials. While, of course, as you can imagine, in metals, the situation is completely different because the electronic occupation are allowed to vary with continuity around the Fermi level, and this implies that you can have a finite contribution from eigenvalues that are very, very near, and so comparable with the phonon frequency. And this denominator is very important because this function will become very, very big. So the real part of the phonon self-energy will become very, very big around the poles of this, so around the zeros of this denominator here. And now let's talk a little bit about what we can do to have an easier treatment of this term. So one of the first things that we actually do is to not retain the frequency dependence of this self-energy here and go into what is called an adiabatic approximation, where we actually obtain a static expression for this correction to our phonon self-energy. And I have to say that in most cases this approximation is accurate, just because the frequency dependence of the self-energy is usually negligible. However, I have to say, and I will show you after, that it's not always the case. For example, in some intercalated graphite compounds, it's very important to retain this dependency here. And okay, we will talk a little bit about this later. But before, let me just say that if you neglect actually this term here, so the frequency dependence of your self-energy, what you get is basically a nesting condition. That is, this term will become larger when the two electronic eigenvalues are equal. So basically, what you're saying is that the real part of the phonon self-energy will become non-negligible, so very important, in cases where the electronic eigenvalues are equal. So this gives you what's called the nesting condition, and this means that as long as you have around the Fermi level, because here you have the occupation, so you are basically waiting for you want to be near the Fermi level to get finite contribution. you will have a lot of contribution when there are a lot of states that are there and that they have the same energy. So essentially, it's very important that you have a high density of states and what is called a high nesting in your Fermi level, in your material, to obtain a finite effect due to the electron-phonon interaction. And we will show some example now. Also consider the fact that this expression here is always positive, just for causality reasons, and this means that your frequency, which gets corrected by this term here, essentially is diminished by this term here, always become smaller due to the electron-phonon interaction. And this softening, how we usually refer to this effect, is visible in many different materials. For example, in many TMDs or many charge density wave materials. As we will see now, this is also depending on the dimensionality of the material. So let's do a very simple example, just to be even more, just to forget about the mass for a moment and just understand the physics of what we are doing. So assume that you have just one parabolic band and one phonon mode. This real part of the self-energy is just the square of your electron-phonon matrix element multiplied by the Lindner function, which is the susceptibility of your material. And this correction here is something that, if you evaluate it, it diverges in one dimension. So you have a divergence of the chi0. It gets like it's discontinuous at Fermi level in 2 dimensions, and it's there, but it's almost moot. Its second derivative is not analytic in 3 dimensions. So this is important because, as you can understand, for example, think about the case in 1 dimension. In 1 dimension, you will get a divergent contribution due to the nesting factor at even a very small electron-phonon coupling. So it's sufficient to have a very small electron-phonon coupling to have an instability, because of course this would renormalize your frequency and will cause instabilities in your system. So depending on the dimension, of course, and on the entity of this factor here, you can get very particular and critical behavior on your system. Of course, this depends also on the temperature. So this divergence here is for 0 Kelvin and it gets renormalized. However, the contribution is always negative and is always going to diminish your frequency depending on all these factors, let's say. So of course, as we saw that this goes like that, it's clear that the real part is just the inverse of that, and that you get this kind of corrections to your system. So consider that this effect is present in your density functional perturbation theory calculation. Just to come back to what it was asked some lectures ago about the presence of electron-phonon coupling in your calculation. So this is also true for SSCHA calculation. Let's say this term onto the frequencies and onto the total energy of your system are included, because the electron-phonon interaction is nothing but the way your quantum system responds to a movement of the atoms. And this is important also to mention that as you get closer to the critical point, so imagine that the frequency goes actually to 0 in your harmonic approximation. But as you go close to the critical point, your Born-Oppenheimer energy surface is getting increasingly anharmonic. So that term there, you should be really careful about considering the harmonic result in proximity of when this frequency becomes 0. Because of course your potential will be very anharmonic because you are close to a transition. And so you will need to include anharmonic effects to recover a quantitative understanding of the phenomenon. And of course, your anharmonic treatment will contain both the anharmonicity of your Born-Oppenheimer energy surface and the electron-phonon contribution to the frequency renormalization. So this is a real case scenario when you have a material which is zirconium tritelluride having one-dimensional behavior, so one-dimensional periodic chains, and you will see that if you measure with the inelastic X-ray scattering the phonon dispersion as a function of the temperature, this becomes increasingly close to 0, and you observe exactly what you would expect. So a progressively bigger correction and the insurgence of essentially of instability in your system. And this is a typical charge density wave material. So in this way, it's like you can give some microscopic understanding on this kind of observation, let's say. But what if we are so in a higher dimension? So it's not simply a 1D material, but a more complicated material. Well, in general, you will have a Fermi surface, and in order to understand how important is this effect, you will have to consider how much of this surface is nested about a specific Q vector. Nested means that if I start from here, for example, and I apply the phonon wave vector, I come to another portion of the Fermi surface which has an eigenvalue. So the more, like for example, imagine two parallel lines, you will have a perfect nesting of the wave vector separating the two lines. So here you have some nesting, and of course what you can do is you evaluate this nesting. So as you see, as you saw, the correction to your frequency is something that depends both on the electron nesting, so on the susceptibility and the intensity of the electron-phonon interaction. So imagine that both of them are present, you can get an important effect on your phonon frequencies. So this is something that was actually this is a very old idea that was introduced by Kohn, and essentially this regards the presence of softening anomalies in your phonon dispersion, and this can be seen even in three-dimensional materials where you don't have this pathological behavior, but still you have a term that involves the nesting at the electron-phonon interaction, and you can see that, for example, if you go onto some very standard solids, you will see that in some cases you observe that the frequencies at very specific points in the momenta are showing essentially a renormalization of the bare frequency, and essentially this is a measure of the intensity of the electron-phonon interaction. This can be in many different points in your brilliant zone, and depending, of course, on the specific Fermi surface that you are considering, so on the specific material, the position of the Fermi level. So you also see here why these nesting effects are so dependent on the Fermi level, because essentially they depend on the shape of your Fermi surface. And yes, of course, in materials showing superconductivity, electron-phonon coupling superconductivity, you will see a lot of this nesting because, of course, the electron-phonon interaction will be big, and so there is a high chance that as soon as you get some kind of nesting due to the bare susceptibility of your system, for example, here in magnesium diboride, you will see that you have these cylinders here along the gamma dispersive line in the brilliant zone. You will see that essentially as soon as you get some nesting vector, you will have a kink in your phonon dispersion, kinks that are measured and are seen in a standard way, and are a way to understand if superconductivity in some material is due to the electron-phonon interaction, because if you measure electron-phonon interaction, you can say, well, okay, the electron-phonon interaction is enough to guarantee that the superconductivity that I measure is microscopically originated by this interaction here. There is one problem, of course, that this case here is very easy because it's a case where essentially neglecting the frequency dependence of your self-energy is not very problematic. But there are cases, as I was mentioning, where you have to retain this dependence. For example, as I was mentioning, this is an intercalated graphite system, and you see that if you actually put in your calculation the frequency dependence in the self-energy, you get completely different phonon dispersion. So you have to be careful, especially when you have nested materials presenting phonons that are nested at very high frequency, because of course if the frequency is very high, you're not evaluating anymore the nesting at the Fermi surface, but you're evaluating essentially how electrons at the Fermi surface are coupling with electrons that are distant omega frequency from the Fermi surface. So essentially it depends really on the entity of this frequency. So if this frequency is large, you are moving a lot into energy. And also if the electron-phonon is large, this effect will be very large. And this is the case, for example, for many carbon-based materials because they are very hard, and so the frequency are high, and the deformation potential is very big for some modes. So I will finally come to the imaginary part now of the self-energy, the phonon self-energy. The imaginary part of the phonon self-energy is maybe the most important quantity when you go on and study superconductivity, and we'll see the reason very soon. However, let me start by just looking at this expression here and say that, okay, this is still a quantity that can tell you information about the lifetime of your particle. As I was mentioning before, this is just one contribution to the lifetime. As we saw in all the other lectures, other contributions stem from the, for example, for the phonon-phonon interaction, and so from the anharmonicity. But let us consider a case where, okay, let's first come to an expression which is widely used in superconductivity community. So basically, this expression here that contains electronic occupation and a delta at the difference of the eigenvalues minus the phonon frequency is usually what we usually consider actually is 4 times this expression, and also we plug a frequency in front of it, and we divide by the frequency the electronic occupation, just because with this trick here, in some conditions where the temperature dependence of your line width is not that big, you can actually substitute this with a delta function onto the Fermi surface, and you get this expression here, which is the Allen-Phonon line width, which we usually use to measure the imaginary part of the phonon self-energy. And this is very important because if you look at here, this has 2 delta functions in proximity of the Fermi surface. And this is kind of tricky because when you do numerically, you need to be careful because you are putting 2 deltas there. So you have to be really, really sure that your Fermi surface is well described. Otherwise, you will get really unconverted values. So this is the reason why usually people, including us, are interpolating electron-phonon matrix element. The reason is just that you need to be very, very careful about the Fermi surface. So you need to be very sure that your calculations are convergence. Also, once you have this expression, where we usually also neglect the dependence on the frequency, as I was mentioning before, you get this expression here for the phonon line width, and you can define actually the electron-phonon coupling at a single phonon momentum in terms of this line width here, and you will see that this expression for the electron-phonon coupling is essentially, is proportional to the Allen line width, and also tells you the importance of the density of states, because here you have, like, imagine that these delta functions are independent. These are just 2 times because there's sum. Imagine that this G is constant, basically. So you have this sum onto double delta, and this gives you just the square of the density of states. So at the end of the day, the lambda at a certain Q will just be depending more or less linearly on the density of states, on the phonon frequency as well, and of course on the electron-phonon matrix element. So you looking at this expression here, you can understand why measuring the phonon line width essentially gives you the information about the electron-phonon coupling. Also, consider that this electron-phonon coupling here, if you integrate it, or rather, if you average it in the Brillouin zone, this just gives you the electron-phonon coupling parameter, which then we plug into most of the expression that we use for superconductivity. So this tells you that in cases where other effects are negligible, and in particular I'm thinking about anharmonicity, measuring the phonon line width is giving you information about the electron-phonon coupling. And this is the case, for example, in MGB2, and when essentially the idea is the following: if you see that your calculation is matching well with the experiment regarding the phonon line widths, you can conclude that indeed the system is not anharmonic, and that essentially it's correct to infer information about the electron-phonon coupling from the line width measurements. If, however, the experimental line width is much bigger, this means that essentially the line widths that you measure are not just due to the electron-phonon coupling, and you cannot infer information from the experiment simply by looking at the phonon line width. This is the case, for example, for many transition metal decalcogenides. So, in this case here, which is magnesium diboride, the theoretical calculation in the red line is basically identical to the experimental measurements given by the black dots. And so we conclude that this material is weakly anharmonic, and the electron-phonon coupling is responsible for this broadening that we see in the spectrum. So I come to the last part of the presentation, that is, okay, why all of this is relevant for superconductivity? Why are we actually interested in this parameter? And to show you this, I want to start from giving you a perspective on what a superconductor is. So a superconductor is a material, is a phase of a material when you have zero resistivity, perfect diamagnetism in the sense that you have no magnetic field inside the material, and also a macroscopic coherence regarding quantum effects. So you get to see quantum mechanics in a macroscopic fashion. The first microscopic understanding of superconductivity culminated in 1958, with the BCS theory. And essentially, the idea behind the BCS theory is rather simple, while the math is very complicated. But the idea is very simple, because the idea is simply that the interaction between electrons can become attractive in some specific regions of wave vectors and frequencies. And this effective attractive interaction can cause electrons to behave coherently between them and to, in some way, and to form new quasi-particles and to be bound. This effective interaction is not the Berk-Coulomb interaction in most cases, and also in the BCS picture, this was not the Berk-Coulomb interaction, but was rather an interaction that was stemming from the mediation of phonons. So essentially, you get an Hamiltonian. The BCS model is valid for whatever microscopic origin of your interaction, provided that we are in a perturbative regime. And essentially, the idea is that if you plug an attractive interaction into the electronic Hamiltonian, you will see that a solution appears that opens gaps in correspondence to the Fermi level, and that this gap is essentially proportional, which is the superconducting gap, is essentially proportional to the critical temperature by which the material loses its superconducting properties. So, of course, this doesn't tell you a lot about the importance of electron-phonon coupling. But as it turns out, if you do a microscopic treatment of this kind of phenomenology in solids using the Migdal-Eliashberg equation, one of the most understood and well-studied channels for this interaction to become attractive is that this interaction stems from the mediation of phonons. So if you do a complete treating of this problem, which I won't do here because it's very, very long and complicated. However, you will come to those that are to equations that are called Migdal-Eliashberg equations, and besides, essentially this equation comes from the writing the self-energy from this propagator. This is a notation that involves essentially the time ordering of field operators that are now not single particle operators but two particle operators, and essentially superconductivity stands where these off-diagonal terms acquire a finite expectation value. However, what I wanted to show you is just that in order to have a solution, to determine the solution for your superconducting gap, it's very important that you have that this quantity inside the parentheses is positive. And this quantity is nothing but the electron-phonon interaction, as you can recognize here by the presence of the Eliashberg function that we introduced before. And to this, you have to subtract the residual interaction in the superconducting state, which is usually very difficult to calculate, and which we usually treat in a parametric way, in a semi-empirical way with a number. This is possible because this number is, in many cases, is constant and can be considered basically a fixed value. And essentially what you get is that all these equations can be solved once you know this is the Matsubara representation, the imaginary frequency representation. And this can be solved by the knowledge of just the electron-phonon coupling Eliashberg function. So at the end of the day, if you know the electron-phonon coupling in your material, you can solve the Eliashberg equation. Note that this end here can be, in some cases, in the isotropic case, it's just indicating a frequency, but you can also sum here onto the k points, and you will get, like in the previous BCS equation, you will get also a dependency on the k point. So essentially, you could have a gap that depends on the k point in the most general case, but it's true that in many cases you can just do an isotropic treatment on this gap and have let's say, an isotropic gap that gives you essentially just the average gap, and is a good approximation to the real superconducting solution in your system. And furthermore, in an even more simplified way, what you can do is just to use a semi-empirical parametrical formula that was fit by Allen Dines and Macmillan in subsequent papers. And essentially, you will see that the critical temperature, if you're interested in a very practical, let's say, description of your superconductor. So let's assume that you're only interested in the critical temperature of your superconductor. This will, in a regime where lambda is not too big, let's say, you can just write in terms of this lambda, which is the sum over q of that lambda q that I defined before for the phonon, and the mu star, which is the Coulomb repulsion parameter. And this is a good approximation and describes well many different cases, and it's always a good reference when you want to solve for superconductivity. So in general, what people do to different degrees of complexity is either they solve the Migdal-Eliashberg equation in an isotropic fashion, or if you have reasons to believe that the k-dependence of your superconducting gap is not important, you solve the isotropic version of that equation. Or if you are just interested in an estimation of your critical temperature, you can also go and solve this equation here. In any case, the important point is that the electron-phonon coupling parameter is always what is determining actually the superconducting critical temperature. So it's the central quantity of the theory, and what you really want to know if you want to understand whether the system will become superconductor or not. So I will just leave you some take-home messages, very simple. So I hope I convinced you that the electron-phonon coupling is involved in many quantities, actually in most quantities in solids. These affect both the electronic and phonon spectral functions. It's the driving mechanism for conventional superconductivity, and it's also relevant for many technological applications due to the fact that it's responsible for many transport properties and optical properties of material. So thank you very much.